On the left side of your screen, you see a state-of-the-art water physics simulator. And on the right side of your screen, you see predictions from a graph network. Now, it is no easy task to build an effective water physics simulator because it's not as simple as treating water particles as billiard balls. This left side simulator is from the Splish Splash project. And to give you an idea of the complexity, that project README has a reference to 18 different papers on topics from pressure solvers to viscosity, surface tension, drag forces, and so on. For the graph networks, no fancy physics is required. These models were learned just by looking at the particle positions from the simulator data. So in essence, the model learned about the physics of fluid by mere observation. And this doesn't just work for water. It also works for sand and for goop and for rigid bodies floating in water. It even works if you mix everything together and make random hippo shapes. And it's worth pointing out that the sand simulator and the goop simulator that generated the ground truth data were their own specialized simulators that were designed specifically for modeling those types of materials. The water simulator wouldn't be sufficient for doing that. But the graph network process remains the same. They generalize to multiple types of materials if you have the ground truth data to train them on. In this video, I'll talk a little bit about physics simulators and why learnable differentiable physics simulators is cool. But I mainly want to dive deeper into the methods of this paper as a mechanism to help us understand where graph methods are useful and why they're useful. I actually also got to talk to Jonathan Godwin, who's one of the authors of this paper, and he's from DeepMind. So stick around to the end of this video to see parts of that interview. And let me also mention I have a Discord server, mailing list, and blog. So if you'd like more content from me, you can find them there. I'll put a link in the description below. Why is this cool? Well, we can conceivably use this simulation data to train models that make predictions that are of similar quality as the simulators, but without having to run the very computationally expensive simulations. So in this talk from Daniel Holden at Ubisoft, you see that he has this ball interacting with a squishy bunny. And using the physics simulator, it can only run at a half a frame per second. But by training a predictive model on that data offline and then using it in real time, he can have up to 2,700 frames per second. So he doesn't use any of the techniques that we'll be describing in this paper, but it just shows the possible applications of having these machine learning driven predictive models from simulation data. There's also other papers that show orders of magnitude speed up specifically for fluid simulations where the models are much, much faster than the original simulators and of similar quality. We also see success in cosmological physics research where they'll have a physics engine using the most accurate methods, and that works really well but is super slow. And then they train a model on that data, and it outperforms other simulators that use the next best approximation scheme that's not quite as accurate. And those machine learning models actually outperform in terms of predicting the actual cosmological structure than the other faster simulators that were used. There are also really interesting applications in robot control and planning. So if a robot has a physics engine, it can think through and simulate what the physical outcomes are going to be of its actions. But since these physics engines are also differentiable, that means they can take a desired final state and apply gradient descent on them to optimize its decisions and actions that it takes. And this is such a cool topic that deserves its own video, so I won't talk any more about it here. Using machine learning on simulation data to have this predictive model that's like a pseudo physics engine is not a new idea. What's new here is that this particular set of techniques works so well across a wide variety of materials and conditions. And it also generalizes super well outside of its training domain. So for instance, you can train it on 2,500 particles, and then when you scale it up at test time to over 25,000 particles, it still works really well. or if you add in much more complex boundary conditions or mix and match materials in weird configurations, it just keeps performing very well. So the main technique underlying this is of graph networks. And this is distinct from graph neural networks. The graph networks is a more general concept. And there's this super interesting paper from the DeepMind group called Relational Inductive Biases, Deep Learning, and Graph Networks. And in that paper, they talk about a bunch of different contributions in the field, and they show how they're all kind of a special case of this new framework or formalism that they call graph networks. So this paper on the physics simulation is from that same research group. And they're just doing a great job like pioneering this field and doing these interesting application areas, particularly around physics simulation and robot control and planning. Let's start by giving a high-level overview of all the steps involved. So the first step is to construct the graph. And the way that's done is that particles within a particular small distance from each other are given edges. So particles only interact with their immediate neighbors in space. And then features are assigned to each of the nodes and each of the edges. So each node gets features such as its mass or its other material properties. And it might have things like the velocities of the previous 5 time steps. And then the edges have features like the distance between the two particles that are interacting, or the spring constant, if one exists. The next step is to do message passing. So if you haven't studied message passing, you can check out one of my videos on label propagation or graph convolutional networks. But message passing is just when the nodes in the graph send messages to the neighbors that they're connected to. And then each node receives these signals from their neighbors and uses them to update its representation of itself. So this is the interaction piece. So this step is what makes all of the particles interact with their neighbors and get a new updated state that reflects that. The third step is then the decoder, which takes these new updated states and turns them into acceleration vectors. So this is what the final output of the network is. It's to predict the acceleration of the particles in the current time step. And then the last step is to use those acceleration vectors and update the state. And this is just physics 101, where the new velocity equals the old velocity plus acceleration times the time step. So this tells you where the particles are going to move into the next frame. The authors break this down as being 3 different modules. The first is the encoder, then the processor, and finally the decoder. So the encoder is responsible for constructing the graph and initializing the node and edge features. But one detail here is they don't just use the raw features. They first pass them through dedicated neural networks. And that just projects them into some new space that hopefully facilitates learning in the downstream tasks. So once you have these neural networks applied to the raw features, these are the initial embeddings for both the nodes and edges. Now keep in mind that no interactions between particles has happened at this point. The second step, which is the processor, is what does the message passing. So the number of graph network layers you have determines how far each message can propagate. So 3 layers means you can go 3 hops away from a node. And the authors note that this will likely need to scale with the complexity of the interaction that's trying to be modeled. And at the end of this process, you have updated embeddings for each of the nodes that now take into account its m-hop neighborhood, where m is the number of graph network layers used in the processor. And then finally, the decoder is what translates these updated embeddings into acceleration vectors. This seems like a reasonable model of the world, that in some narrow time window, these particles interact in a way that influences their future behavior, and then they move, and then the whole process starts all over again. So what is it about graph networks that is key to making this work well? I think it's worth reflecting on this, because hopefully by understanding it, we'll have a better intuition for the types of problems that graph networks are well suited for. So consider for a moment what you would do without graph networks, maybe just regular neural networks. What would the inputs and the outputs be? So the first challenge is that particles are going to interact with different neighborhood sizes. So one particle might only interact with 5 particles, and another might interact with 20. So how do you handle that? You could do some max neighborhood size and sample and pad or something like that, or maybe you have a recurrent neural network that you apply to get a fixed length output regardless of the size of neighborhood. But what happens if you take an identical neighborhood and then you change the ordering in which you consider them? Well, neural networks won't let you just swap things around and give you the same outputs. They're not permutation invariant. The same is true for RNNs. But that's not how the physical world works. It doesn't matter in which order you add up physical interactions. 1 plus 2 is equal to 2 plus 1. But neural networks won't allow you to just swap the inputs around in that manner. Graphs do a few useful things. The first is they encode what interacts with what, which is obviously super valuable. The second thing is that they combine neighborhood information in a way that's permutation invariant, which means that for the same neighborhood you get the same output regardless of how the data structure is ordered. The third thing is that they're very data efficient because they have lots of examples that all share the same network parameters. So all the particles are using the same model parameters. And the model gets to see lots of different interactions and lots of different scenarios at each time step. So whereas a image classification problem, you might get a single label for an image, in our problem, the model has to predict the accelerations of every particle in the system at every time step. And each one of those errors helps it learn its parameters. Some of the coolest results are in how this model generalized to scenarios far outside its training setup. So whereas it's trained for 2,500 particles at a single time step, when it's applied to 28,000 particles for thousands of time steps rolled out, it's still generating sensible results. And the way it's able to do this is it's exploiting the power of the graph networks and the properties that it has. So if you've been able to effectively model this system as these localized interactions, then it's not surprising that if you add more particles, it still works well because it's just more of the same interactions. The key is that properties of the physical system and its interactions are encoded into the learning problem itself, and these are known as inductive priors. So we know from Newton's law that mass times acceleration is equal to the sum of forces, that we just need to add up the contributions of all these pairwise interactions, and that's baked right into the graph network approach. We also have the permutation invariance baked in, and we have that the only important interactions come from things that are localized baked in. And more subtly, we have that interactions can be discontinuous baked in because the graphs are dynamic. So between any two time steps, the neighborhood for a particle might be different because particles have either moved in to the proximity criteria or moved out, and that interaction is discontinuous, much like in the case of a collision. So I'd originally planned on stopping the video here, but I got an awesome opportunity to talk to one of the original authors of this paper, Jonathan Godwin. And in that conversation, he helped me understand that their use of noise, which was a detail I'd kind of glossed over when I read the paper, is actually critically important to understand why this model generalizes just so well. And it's a very distinguishing feature. So if you would like to hear about this and some other great insights from Jonathan, you can check out that interview right now. Jonathan, thanks for taking the time and talking to me about this paper. Super interesting. Can you start by just introducing yourself a little bit and where you work and what you do?
Yeah, absolutely. So, I'm Jonathan Godwin. I'm a research engineer at DeepMind. I work on the sort of structured intelligence team at DeepMind and working on sort of graph nets and simulation. I've been at DeepMind for a few years now, and before that I worked at some startups, also working in machine learning.
Awesome. So I guess we'll get right into it. You mentioned that group had worked on these sorts of methods before, and I know interaction networks came out of Peter's group or somehow associated with him. So what's different here compared to these prior approaches that, this isn't the first time that these graph-based methods have been applied to physics simulation-like problems. So what do you think is the key kind of difference here?
Yeah, so I think we've got a few contributions here. So I think one is that we're trying them on I think large scale simulations, or well, larger scale than have been done before. So I think one of the contributions that we took something that we thought worked on smaller problems, and we could see if it worked on larger problems that we thought were more complicated, which is these simulations. So I think that's one thing, which is just taking something small and scaling it up, and actually it works pretty well. I guess that's a trend that you see in a lot of areas of machine learning. And then I think another contribution which made it work well is that we've added random noise to the input velocities and asked the model to correct for this noise. And you can kind of imagine this like a little bit like data augmentation. You know, we're sort of sampling as if the model has got something slightly wrong and asking the model to learn to correct for itself. And we noticed that this made quite a big difference in avoiding sort of large accumulation of errors during rollout. So, you know, often if you just train on a sort of single step, you'll make a small errors, and then eventually you'll get so out of the distribution of your training examples that the model has no idea what to do, and then you just get these catastrophic errors. And I think adding this random noise meant that the model sort of learned to be a bit more robust. Mm-hmm. And so we thought that at least in our experiments, we found this was quite important. So I think those are sort of two areas where I think we pushed the boundaries, and combining them led to these sort of what I think are great results.
Yeah, totally. So the other papers that were referenced, like DPI nets, they were just more specialized, and you know they had a lot of stuff that was in there to make it work, but then it sort of limited the domain. But something about your approach had made it work across a broad set of domains and not need these kind of fine-tuning tweaks. Do you think that comes down to the adding the noise to the inputs, or do you think there's some other aspect of the design of this that made it generalize better?
Yeah, I mean, so I think that the majority of it came down to the noise of the inputs. I think that some of the things that more broadly make GraphNets generalize well, like the locality. You know, we've got 10 steps of message passing, so that kind of means that 10 steps from your radius of nearest neighbors. You know, that's how much communication you can do for a single node. But that also means that you don't need sort of global information. So the size of your simulation can continue to scale and can continue to work, because actually it's only local information that matters for the prediction, at least in these simulations. For other simulations, you can imagine that that's just not the case. So I think that's general to GraphNets. I think really for us, like we sort of found this noise. It's a very simple thing. It's kind of like this one simple trick makes your model work. But I think for us, this was really the most important thing to gain that stability, which I think the other models did by adding in these constraints.
Yeah, in some sense, it seems intuitive, but in another, just thinking about physics and the so-called butterfly effect, right? That like these small changes in initial conditions can lead to totally different behavior on longer timescales. So I was struck that by doing that, you were still able to faithfully recreate the simulation data, as opposed to generating a sort of equally plausible but different reality or outcome. Do you have any sense for why that's the case? How come perturbing these things doesn't lead to just a divergence of a different type of behavior but still realistic?
Yeah, because I think in some ways our training regime kind of gives you a noisy input, and you kind of need to denoise that input and then predict what would happen from that denoised input. That's sort of, that's in some ways the way I think about it. So our training regime doesn't say I'm going to predict the next step, and then I'm going to ask my simulator to run from this predict the next step to the next step, and I'm going to use that as my target, which I think would give you this sort of variation in rollouts. We're really asking the model at training time to snap back to the trajectory that we've kind of messed up with this noise. And I think that leads to quite high fidelity simulations versus sort of plausible simulations across slightly different trajectories as you're accumulating different sort of as you're accumulating error and then getting into areas of the training distribution which you might not have seen in the past.
So I guess the training task is subtly different. It's not necessarily predict the acceleration, but it's predict the correction that leads to the correct acceleration because we added this perturbation. Is that right?
Yeah, that's right. You've got to learn to add that correction in. That's correct. Yeah, and then I think that correction is what gives you the high fidelity simulations.
That's really interesting.
In fact, you can test this out on we've just open sourced the training code, and we have this as a parameter, so you can see the effect of sort of going from no correction to full correction. And you can see the effect that it has on the rollout. So if you would like to try that yourself.
That's awesome. Yeah, I forgot to mention that you guys did just open source this. I know you had said in the paper you were going to, but that's finally out. So I'll make sure to put a link to that in the description. So onto the application. What do you think is the most exciting, at least in your mind, application areas of this type of work? Is there like a broader problem that the research group is trying to solve, or is it just sort of I had identified an interesting use case and it's sort of the end of it now?
Yeah, it's a really good question. So I think there are lots of interesting applications that you might think of. I know a lot of people, when we talked about the model, are quite interested in things like molecular dynamics and mesh-based simulation, or perhaps using the simulation as a tool in a reinforcement learning agent, as a model-based reinforcement learning. I think all of these are really interesting directions. I think that the one thing that our paper did show is that these sorts of simulations can scale to fairly large simulations. And so maybe at some point for sort of scientific questions where simulations are really important, maybe you can have a learned simulation along the lines of the sort of thing that we've done here. But I think all of the problems that I mentioned have new challenges to them that aren't quite solved by a paper. Something like molecular dynamics, maybe instead of pairwise interactions, you've got three-way interactions. You have long-range forces, which might not be catched with multiple steps of message passing. And you have, the problem of having to take maybe billions or millions of time steps to let's say fold a protein, right? Like that's something that really isn't solved by using a graph net. So I think that this is one step, and to have real world impact, there are a few other challenges that need to be solved.
Great. So one possible application I'd seen where people were training models on simulation data was for like real-time graphics and simulation. Do you think this is a path forward for that? Or I know there were some references, I don't remember if it was in the talk or the paper itself, that it wasn't much faster than the simulation, but there wasn't like a fundamental problem. It was just that hadn't been optimized yet. So you're probably uniquely qualified to talk about this piece of it.
Yeah, so I think that certainly if we had spent a lot of time optimizing the code, we could have made the inference time faster, and then I guess it could have been faster the graphics and the underlying simulator. Particularly things like the nearest neighbors lookup. There are certainly ways that you could make that faster. That was in our paper done on CPU, whereas you could do some sort of fast nearest neighbors scheme on GPU in the inference loop on device, and that would be a lot faster. So I think certainly like you could say that these things are faster. I think maybe you could also do things like maybe have a sort of coarser model. Maybe that could be faster still. Maybe you could just add a sort of efficiency by taking sort of multiple time steps. So coarse time steps. So I think that's certainly a sort of area, but I guess the sort of the challenge to that is if you're thinking about real-time graphics in the sense of really high quality rendering, we didn't go into that rendering zone, and if the rendering is actually what's taking a lot of the time, then maybe this isn't going to be any faster. What we've done is we have a particle-based simulation, and we predict the positions of particles in the next space. So if that's the expensive bit, then we're going to be faster. But if the sort of high def renders, which we showed, which you can derive from our particles, if the high def renders are taking a lot of time, then we're not going to have much speed up for you.
So what are you using for implementing these message passing? Like DGL is a popular framework, but I think you guys had built something on top of TensorFlow, like a GraphNets library yourself, right? Are you responsible for maintaining some piece of that, or?
Yeah, that's right. So our team, Alvaro, one of the co-authors on the paper, builds and maintains a GraphNets library on top of TensorFlow. So, but in terms of sort of our work and how we managed to make this performant, I think a key part of that was our usage of TPU. So I think this is one of the first times, or an interesting thing about this paper has been the fact that we distributed a single graph across multiple TPUs during training time to speed up training. And a lot of the infrastructure that's built into TensorFlow makes this pretty easy. I think some of the stuff with TF Estimator means that you can train these really, really large models. And this allowed us to train some of our largest simulations in a day or two, where it would normally take like a week.
Oh,
and this,
wow.
This was made our iteration cycle a lot faster, and I think points in the future to really large scale learned simulations on TPU pods, or large scale interconnected GPUs like OpenAI use for their language models. So I think that's an exciting direction in terms of the hardware and the sort of engineering for graph neural networks.
So I guess these sort of lend themselves easily to partitioning across GPUs, since the definition of the graph is locally spatial, and you have these spatial coordinates. So it's sort of easy to partition across multiple GPUs, I'd imagine. Easier than a generic graph, anyway.
Yeah, that's right. So there's some locality structure that means the communication across GPUs is less than it would be in a totally random graph. And I also think that graph networks in general lend themselves to this sort of computation because you apply a model to every node independently. So that's a very easy thing to parallelize. Whereas yes, the convolutional network, if you've got to you've got a slightly more difficult parallelization scheme, right? You've got to do maybe pipelining, or you've got to have model parallelism, and that's a slightly more difficult thing to wrap your head around. But I actually think graph networks are a good example where you can do some sort of you can distribute your model across many chips in quite an easy to understand way.
Yeah. So what do you think are the important open questions of this line of work? And are there like any key challenges to overcome that are sort of generic, or do you think they're sort of application specific?
Yeah, so I think that so I mentioned, I guess, a few of them when I spoke about perhaps the different applications. One thing that was in the paper is that we didn't deal very well with rigid body objects. So we clearly need an improved approach for simulating sort of rigid bodies or elastics. Our approach doesn't really work with those. And I think some of the other things are more fundamental than that, maybe. So with our 10 steps of message passing, we work well with problems that are sort of intrinsically local, but many sort of real applications have this global structure. let's say you've got sort of global long-range forces, which aren't going to be calculated from your 10 steps of message passing. Maybe you need a different architecture for that. That's not going to be in the GNS. Or maybe you've got 3-4-way interactions, and again, that's going to be pretty difficult to approximate with the pairwise interactions of the current graph structure. So I think those are sort of really important things to try and resolve.
Yeah. So what's your intuition for why the rigid body would have an issue? Because to me, that seems sort of straightforward in a naive way of thinking about it. It's just like you kind of memorize the relative position to another particle, and if it rotates, I don't know, like there's only rotation and translation, right? And everything else should be more or less constant. So I don't know why this would struggle there. Any ideas?
Yeah, I think that's a good question. So I think that I sort of share some of that intuition, and I think to a certain extent we saw that. So we have a rigid body in water, and we found that it sort of somewhat kept its shape, and over time it deformed. So the sort of the perfect memorization wasn't there, but clearly some sort of degree of memorization was taking place. So I think that sort of points to the question that there's no hard constraint there, and it seems to be quite difficult to learn that hard constraint. And I think the second sort of question is rigid bodies interacting with one another, so that's sort of collisions. And I think that's a harder thing, because you've really got to propagate forces in some ways sort of long range, right? If you have a large rigid body, you don't have any deformation when they hit towards one another.
Yeah.
They collide. So there's an instantaneous communication from one end of the rigid body to the other. It's really got to be absolutely perfect. And it doesn't quite work like that, right? So that's almost like a long range force. So I think the sort of rigid collisions are a bit more difficult. Maybe you have something like an elastic as well. That seems to me like you've got to have some sort of knowledge about the rest state of your elastic material if you're going to get your model to work well. And there's nothing in our model that says that you should have that sort of information.
Wow, that's very interesting. So outside of this work, what other problem areas have you excited?
Yeah, so I've worked on medical imaging in the past. That was my first sort of project at DeepMind on mammography. And I think that continued work on medical imaging and applying AI to health has sort of the real scope for great real world impact, and it's exciting to see Google do more of that. And so I'm just generally excited to see how that pans out, and all the sort of developments that are taking place in sort of fundamental AI, if you want to call it that, stuff like graph networks or all of the sort of language models. How that applies to the healthcare space. I think that's an exciting area.
Are you working in that domain right now, or just something you're watching with interest?
It's something that I'm watching with interest. DeepMind Health got moved to Google Health, and I stayed at DeepMind. So Google are doing all of the health AI work.
Gotcha.
So I'm looking at interest from afar while continuing to tinker away on things like graph nets.
And this is, I guess, a pretty related question, but are there other researchers or groups that you're following with interest and sort of keeping up with on the cutting edge?
Yeah, so that's always a difficult question, because there's so many groups that are doing interesting things. But I think the people that we collaborated with on this project from Stanford, so Rex and Yuri, they're great people. I think they do great work, and I also want to call out the sort of thanks, because it wouldn't have been the same project without them. So thanks very much to them.
Awesome. Anything else you want to talk about or plug? Like, do you have a blog or anything like that?
Just to sort of stay tuned to what our group is doing. I'm sure we'll be releasing some new things soon along sort of GraphNet lines. So yeah, keep your eyes on the DeepMind blog, or follow Peter and Toby and Rex, who I know are on Twitter.
Got it. Yeah, I'm sure I'll be reaching out to you once I see those announcements. So thanks for taking the time and helping me wrap my head around this. I really appreciate it.
It's a pleasure. Thanks very much for having me.
All right. Take care, Jonathan.
See you.
I hope that diving into this paper wasn't just interesting, but also gave you a deeper intuition for the role that graphs can play in learning problems, as well as the assumptions on which they rely. See you next time.